Today I'm going to present differential kinematics in robotics. This is particularly chapter number 3. Let me introduce myself one time. I did postdoctorate in robotics from South Korea. I am PhD in mechanical engineering and specialization in robotics. Again from South Korea, I did my bachelor's and master's from UT Lahore. I'm interested in wearable robots for hemiplegia and paraplegia patients. I'm also interested to develop assist exoskeleton for cerebral palsy patients and socially intelligent interactive robots and dynamic motion planning for multi-robot system under dynamic obstacles. So these are a few of my interests. I can be followed through YouTube channel. The link is given here. So basically, this is chapter number 3 of Siciliano, and the book written by the Professor Siciliano. So today I'm gonna cover geometric Jacobian and kinematic singularities. I will leave Jacobian of typical manipulator structures to the students. I believe that after going through my lecture, they can possibly solve the problems. If there is any problem, please comment below. So let's begin. Consider an n degree of freedom manipulator. The direct kinematic equation can be written in this form. It is transformation matrix which contains rotation matrix and position of the orientation, position of the frame. Again, 0 vector and row vector, and then 1 just to make it even. So just to make it clear, where Q is will start from Q1 down to Qn for n degree of freedom is the vector of joint variables. Both end effector position and orientation vary as Q varies. The goal of differential kinematics is to find the relationship between the joint velocities and end effector linear and angular velocities. In other words, it is desired to express the end effector linear velocity, which is p dot e, and the angular velocity omega e as a function of joint variables q dot. Just like this, we want to represent an effector linear velocity as a function of joint variables, and jp is some mapping function, and angular velocity omega e equal to jo, function of joint variables, and q dot. In this equation, jp is a 3 cross n matrix. It's relating the contribution of the joint velocities q dot to the end effector linear velocity pe dot, while in 3.3, which is this equation, jo is again 3 cross n matrix relating to the contribution of the joint velocities q dot to the end effector angular velocity omega e. um, let's go ahead. In compact form, 3.3 and 3.2 can be written as this one. This is, we're going to combine it, velocities, which contains linear velocities and angular velocity, and it is a function of Jacobian, which is it is equivalent to Jacobian of q and and being multiplied with q dot. This j is again I'm saying that's called Jacobian, this equation represents the manipulator differential kinematic equation. The 6 cross n matrix J is manipulator geometric Jacobian. This is important to note that we call this kind of representation as geometric Jacobian, which is which is a compact form of linear Jacobian, and angular Jacobian is, and it is a function of joint variables. Now, I want to discuss its derivation. And this theory, which we are going to discuss here, is known as screw theory. So let's consider a time-varying rotation matrix, because this system, if we have, for example, if we have, no, if we have this a robot like this, and we have two joints 1 and 2, and we want to represent this end effector with reference to this point, So rotation matrix, we need to use some rotation matrix. Okay, so but when this joint is over here like this rotation matrix is different for this position, for this orientation. So if the robot is moving, this rotation matrix is constantly changing, and that is why we say that if there is a rotation matrix, if it is a function of time. So let me raise this one. Okay. Uh, in a view of orthogonality of R, one has the relation. We will know that R transpose equal to I, identity matrix, which differentiated with respect to time gives the identity, which is equal to this one. So R dot R transpose plus R into R dot T, R dot transpose equal to null matrix. So let's say that there is a matrix we call S of T, and it is R dot and R transpose. And we call this S matrix as skew symmetric, because if we look at this equation, we can pretty much understand that S plus S transpose is equal to 0, which means S is equal to negative of S transpose, which is the definition of skew symmetric matrix. um, Post multiplying both sides of equation 3.6 by RT. So this equation, if we multiply them with R, we get R transpose R dot T equals to S into T into R. So that allows the time derivative of RT to be expressed as a function of RT itself. So this is very important, that this is a skew symmetric matrix, and this R dot rotation matrix is a function of itself, which contains skew symmetric matrix, and we'll look into that what this skew symmetric matrix actually is. So let's discuss more about it. Consider a constant vector P and the vector PP. Okay, hold on a second. Okay, there was an error. It is not P, it is P dash. I have corrected it. So consider a constant vector P dash, and the vector PP is equal to rotation matrix and being multiplied with P dash. The time derivative of PT is we take P dot and then R dot P bar. So which in view of 3.8 in this form can be written as this. So S skew symmetric matrix with RT, it's just like that, and P bar. So it's interesting that we have represented linear velocity as a function of rotation matrix, skew symmetric matrix, and the mapping function, and some vector from which we want to move, like 0 to 1. So this is the rotation matrix taking from 0 to 1, and this is a vector being represented in that frame. So P dot is equal to this equation, and we're going to represent this omega t into R of t. We're going to represent this S and R in this form, like omega t. And why we are gonna represent S as omega t and cross multiplication? There is a reason behind it, so let's discuss. This also means that matrix operator ST describes the vector product between the vector omega and the vector R rotation matrix P bar. The matrix S of T is so that its symmetric elements with respect to the main diagonal represent the component of vector omega t, because this is skew symmetric. So if we want to represent this omega t as angular velocities of x, y, and z along x, y, and z axis, we can represent this vector in the form of skew symmetric matrix by writing it in a particular shape, which is here. Interestingly, this shape is skew symmetric, which justifies the expression S of t is equal to S of omega of t. So the 3.8 can be written as r dot equals to s of omega into r. So quite simple. That is kind of uh, if you want to relate it, it's quite going to be related with v equals to r omega. So the linear will, although it's not exactly like that, but yeah, you can still pretty much make a vague idea about that. So we have rs omega r transpose, and there is okay, rs omega r transpose, this is going to be equal to s of r into omega. So this is a property which we'll use later, and it's going to simplify our calculations a lot. So this is assignment number problem 3.1 for the students who are attending my lectures. With reference to figure 2.11, which is here, consider the coordinate transformation of point P from frame 1 to frame 0. So this is the point P. We are gonna transformation from frame 0, from frame 1 to frame 0. This is given by this way. So first move in this direction and then move in this direction. P0 is equal to O01. You could see that this vector, and we are actually shifting this frame over here, and then we are rotating it by using rotation matrix. And the vector we are going to represent in this P1 with rotation matrix, and this is aligned to this one. So P0, this one is equal to this vector plus this vector. Now, differentiating 3.12 with respect to time gives differentiation of this vector plus differentiation of this vector. So first r dot and then p dot. Utilizing the expression of derivative of a rotation matrix, which is represented in 3.8, let me show you this one. Okay. um, and specifying the dependence on singular on the angular velocity gives this relation. So we have a dot as it is, we have r dot equals to s and r, and we have our p dot 1 as it is. Further denoting the vector r01 p1 by r01. So what we are doing, we are representing this whole vector, okay, which is after transformation, we are representing it like this one. So you can consider this as some sort of a radius, kind of, yeah, some sort of vector r, which is actually a vector in frame 1 and being looked by, yeah, just consider it r01, and it is and then we can see this equation becoming equal to this one. So we're just putting this this element equal to this one, and as omega is just the cross, is just we're just converting this skew symmetric matrix in a column vector, and this one is as it is. This one is the noun, which is the noun form of the velocity composition rule. So this is velocity composition rule, and it is pretty much useful for the robotics. Notice that if P1 is fixed in frame 1, so if this one is fixed, okay, there was an error, so I have corrected it. So notice that if P1 is fixed in frame 1, it means it is not moving, and it actually means that this point in this frame is fixed, and this whole frame is moving with respect to this frame. Okay, so you can consider it a passenger sitting in a train and just relaxing, and someone is outside the train and it is watching the train is moving. So that kind of scenario. So with this passenger with respect to train is the vector is just constant, but the whole train is moving. So in this scenario, the velocity is equal to this one dot of or its relation dot of frame, which is being represent frame 0 to 0. It's the distance between the two frames, and angular velocity being with the cross product of r01. So this pretty much simplifies the idea. Um, so let's go ahead. I'm sure that it's pretty much it's clear, and if there is any question, please comment below. Now extend this idea to many links. So consider that pi minus 1 and pi be the position vectors of the origins of frame I minus 1 and I. So again, pi minus 1 and pi. Um, so we are watching these frames I minus 1 and I from some another frame O, and also let r I minus 1 superscript and let r I minus 1 subscript I minus 1 comma I, this one, this vector from here to here, denote the position of the origin of frame I. Okay, denotes the position of the origin of frame I with respect to frame I minus 1 expressed in frame I minus 1. So we are this vector, okay, I minus 1 comma I is representing the origin of this frame, okay, with respect to frame I minus 1, and it is being expressed in this frame. So these are three vectors, pi, pi minus 1 and ri minus 1 comma I. According to the coordinate transformation 3.12, one can write this vector pi is equal to pi minus 1 and then rotation matrix of ri minus 1 to r to 0, okay, and ri minus 1 to ri minus 1 comma I. And it is important to mention here that superscript is 0. If it is not mentioned here, it means the superscript is 0. So this is pi 0, pi minus 1 0, and this whole thing is being represented ri minus 1 to 0 and this vector. So in this case it is moving from frame I to frame I to frame 0. So that's what it is going on. Then by virtue of 3.14, which is this equation, okay, this equation, so please note that or velocity of the origin, okay, the velocity of the region of the frame 1 with respect to frame 0, and there is a cross product, and then there is rotation matrix with dot, rotation matrix being multiplied with dot of position vector. So we can write pi dot equal to this vector dot plus ri minus 1 and this vector dot, okay, plus omega I minus 1 cross multiplication of this one. And we know that this one is a linear velocity of point of this point, and we want to represent this velocity. It's a it's the velocity of frame I being with respect to frame I minus 1, and it is being expressed in frame I minus 1. So this point, this thing is the velocity of this point being experienced from here, and this omega I minus 1 is again angular velocity being multiplied with r I minus 1. Just using 3.14. Now let's talk about length velocities. Um, Note that vi minus 1 comma I denote the velocity of the origin of frame I with respect to the origin of frame I minus 1. Concerning link angular velocity, okay, link angular velocity, it is worth starting from the rotation composition. So Ri to 0 is equal to Ri to I minus 1, and then from I minus 1 to 0, and from 3.8. Okay, so let me show you 3.8. This one is 3.8. Okay, so from 3.8, its time derivative can be written as s omega r. So this is going to be the time derivative, and it's going to be equal to s omega I minus 1 ri, okay, plus ri minus 1 s omega s function of I minus 1 comma I, and I minus 1. So this is going to be equal to r dot r okay, hold on a second. Okay, I was confused about this ri minus 1 comma dot, and then ri, and then this one's dot. So it turned out to be that if you take its dot, put its value over here, and then multiply it with ri minus 1, with r minus 1 into I, this becomes ri from I to 0. So it becomes equal to this one. So that is why this dot, the two elements are not being represented here. So if you take the dot of ri minus 1 here, and then you input its value and then simplify it, you would have this term. So next, let's put this ri minus 1 over here, and take r I minus 1 subscript ri dot, and it's going to be equal to this one, where omega I minus 1 subscript I minus 1 comma I denotes the angular velocity of frame I. Okay, frame I with respect to frame I minus 1, and it's being expressed in frame I minus 1. So that is the angular velocity. um, okay, so let's discuss this term, and let's see how can we simplify it. So let me write this term over here, and it's pretty much clear that I can write this term, particularly this one, as in this way as well, because R transpose R is equal to 1 is equal to I, sorry, it's equal to I. In view of property 3.11, which we discussed here, this one. So if there is something like S with our transpose, and and before that there is R, so it's gonna be simple. We can simplify it in this form. So let's use this property over here, because there is R transpose, and before that there is R clearly. So we can write this form as like this. Okay, so we're going to end up simplifying this term as r omega m, and after that this term which would be left, we can just write it as ri. So that's what it's here. Then 3.17 becomes this r dot s being multiplied with ri is going to be equal to this one, and s function of rotation matrix and omega and ri, leading to the result that omega I, okay, is equal to omega I minus 1 plus ri minus 1 and omega I minus 1 comma I, which means that omega I is equal to omega I minus 1 plus omega I minus 1 comma I. It simply means that it means that the which gives the expression of the angular velocity of link I as a function of angular velocity of link I minus 1. So it means that if there is if this is frame this is frame I minus 1, okay, and this is frame I, okay, the velocity of this frame is equal to the velocity, okay, is velocity of this frame, okay, and okay, one more time. um, it means that if we want to measure the angular velocity of omega of this frame, it's going to be equal to as a function of this frame velocity, angular velocity. It's going to be angular velocity of this frame plus angular velocity of yeah, angular velocity, wait a minute. Again, angular velocity of frame I is equal to angular velocity of this frame I minus 1, okay, plus the angular velocity of this um, point, the point which is whatever we are representing in this frame, expressed in this frame. So it's going to be quite complicated. Let me state it one more time. Um, it's really angular velocity of omega I. We are representing it as a function of this, as a function of this frame. Okay, so it's going to be the angular velocity of this frame, okay, plus angular velocity of this frame being experienced by this frame. So that is why it's going to be like this. So omega I minus 1 plus omega I minus 1 comma I. So in general, we are seeing this angular velocity of omega I from some frame over here. I'm going to call this frame 0. Okay, so we are seeing this omega I minus 1, and then we are seeing this omega I minus 1 comma I. So that's what it is. We are seeing the angular velocity of this frame from this frame, and we cannot directly see it, so we are experiencing it by the information this frame is providing us. So that's what this equation means. The relation 3.16 and 3.18 attain different expressions depending on the type of joint I. So there's a difference in definitely different expression for different joints, like for example prismatic or um, revolute. So let me erase that. So for prismatic joint, since the orientation of frame I with respect to frame I minus 1 does not vary by moving joint I in case of prismatic joint, so omega I minus 1 is going to be equal to 0, and the linear velocity is going to be equal to um, okay, I'm sorry, there's a mistake. I have corrected the mistake. So the linear velocity, which is being represented by I minus 1 comma I, again this is a velocity of frame I with respect to frame I minus 1, and it is being expressed in frame I minus 1, not in frame 0. So this one is equal to the rate of change of stroke, which is in case of prismatic joint, and this one is going to be z in zi minus 1, where zi minus 1 is the unit vector of joint I axis. Hence, the expression of angular velocity 3.18 and linear velocity 3.16 respectively becomes omega I is going to be the same as omega I minus 1, and linear velocity pi dot is going to be the linear velocity of frame I minus 1 plus linear velocity because of this expression here, and omega I, okay, because omega I minus 1 and omega I are equal. So in this case, this is going to be in this form. Okay. For the angular velocity, it is obviously for revolute joint, omega I minus 1 is going to be its rate of change of angle, while for the linear velocity, This one is going to be equal to this one, same omega I minus 1 comma I cross multiplication of frame of r I minus 1 comma I, which is nothing but a combination of which is dot product which is a multiplication of rotation matrix and point P being represented in frame I. So this is R. Let me show you one more time what is R. Mhm. So here, so this one is R. Okay, due to the rotation of frame I with respect to frame I minus 1 induced by the motion of joint I. So this one is the linear velocity. Hence the expression of angular velocity 3.18 and the linear velocity of 3.16 respectively become this one. Again, angular velocity because of revolute joint and omega I. Okay, now this one is not equal to omega I minus 1 because they are different. In this case, okay, this one also, this one is omega I minus 1, but they were same. But here this is different, so Ri, that is why it's being mentioned over here. And Ri minus 1 comma I, just like this one. All right. Okay, so this one is going to be the linear velocity. Overall linear velocity, it is going to be pi minus 1 dot plus omega I cross multiplication of ri minus 1 comma I, where 3.18 has been exploited to drive 3.26. So this is the same equation which we have discussed previously. Yeah, over here. Okay. Um, yeah. So for the contribution to the linear velocity, the time derivative of PE can be written as, so it's going to be partial PE by partial QI dot. So this is going to be the summation of all JPIs and QI dot. So um, th this expression shows how PI dot can be obtained as the sum of terms of JPI QI dot. Therefore, by distinguishing the case of prismatic joint QI DI from the case of revolute joint KQI equals to theta I, it is, if joint I is prismatic from 3.20, it is QI dot JP is equal to this one, which is in case of linear Jacobian kind of thing. So linear Jacobian is going to be ZI minus 1. If joint I is revolute, observing the contribution to the linear velocity is to be compared with reference to the region of the end effector frame, figure 3.2. Again, it is going to be in this. So, and in this way, the linear Jacobian is going to be equal to this one. So omega e with respect to end effector is just sum of angular velocities and product of angular Jacobian with qi from I to n. Again, for prismatic joint, qi dot jo is going to be equal to 0, and which means that jo angular velocity is going to be 0. For prismatic joint, this is going to be equal to zi minus 1. And then we have Jacobian computation from GPI to JPN and from JO1 to JON. So for prismatic joint, JPI is going to be like this one. And for prismatic joint, Jacobian is going to be like Zi minus 1 and 0. For revolute joint, it's going to be equal to this one, comma, Zi minus 1. Then we have some simple tips. Zi minus 1 is given by the third column of the rotation matrix. So if you're moving from I minus 1 to 0, so Zi minus 1 is the third column, where Z0 is just to allow the selection of third column, and PE is given by the first three elements of the fourth column of the transformation matrix DE0. So for PE, okay, PE P0. So if you're going to end up having some matrix, the first three elements of the fourth column allows the selection of fourth column, and Pi minus 1 is given by the first three elements of the fourth column of the transformation matrix from Ti minus 1 to 0. So this one again just to allow first three elements of the fourth. Finally, notice that the Jacobian matrix depends on the frame in which the end effector velocity is expressed. The above equations allow computation of the geometric Jacobian with respect to the base frame. If it is desired to represent the Jacobian in a different frame, which is like U, it is sufficient to know the relative rotation matrix U R U, and the relationship between the velocities in the two frames is, you can simply use this rotation matrix and multiply it with both of the angular linear velocities and angular velocities, and then you can represent it in with reference to U frame, which substitutes in 3.4 and gives like this. So you can represent Jacobian in any other frame once it is represented in base frame. For today's discussion, that's end of my today's lecture. I hope you have enjoyed it. If you have any comment, any comment, please let me know, and I'll help you out in understanding it. Thank you very much for your time.